Alright, in the next example, example 4, we're going to look at a continuous case in which, in other words, the charges are continuously distributed over a finite size region rather than a collection of point charges. In particular, we have a rod of length L located on the x-axis. Okay, the left end of the rod is a distance d from a point P, which is at the center of origin of the x-axis, and the other end of the rod is the distance d plus L from this point P, so that the rod has a length L. Now the total charge on the rod is Q. Okay, and if you divide this Q by the length L of the rod, you will get the amount of charge per unit length. Right? This is called lambda. Lambda is called linear charge density. It's defined in the textbook as well. In other words, charge per unit length. We're going to need that in our expression. Okay, the question is, how does one calculate the electric field produced by this uniformly charged rod at point P, which is the distance d from one of its ends? Okay, let's see how we can do that. The idea when it comes to a continuously distributed charge is that we're going to cut it into infinitesimally small pieces, right? Find dE from each little piece, and then we integrate over dE to pick up the contribution from the entire system. So in this particular case, how does one cut this thing up? Well, it's a one-dimensional case, so all we have to do really is just choose a little piece like from here to there. This is x plus dx, right? And this little piece has a charge dq. It is located a distance x away from point P, right? This distance is x. What is the electric field produced by this little piece dq? Well, first of all, the direction of the electric field points that way. Okay, so it's a negative direction. So dE is negative, right? K times dq, it's just a point charge. dq divided by what? This distance squared, so x squared. Now, next, I wish to integrate over dE. The nice thing about this integration is that every little piece dq produces the electric field in the same direction, which is along the negative x-axis. So I do not have to use vector summation. Okay, this is just a scalar summation. But before I can integrate, I must make sure that I get rid of one variable. There is a dq, but there's also an x. I don't want it. I don't want that. I want to express dq in terms of dx, right? And how does one do that? Well, dq is the electric charge contained within this little infinitesimal piece of length dx. Now, the charge per unit length is lambda, right? So therefore, I know that dq must equal to lambda dx, just like q equals lambda times L. Okay, you plug that in here, and then you find that dE is now equal to negative ke lambda dx over x squared. Right? We're now ready to integrate over the entire rod, in other words, from x equals d to x plus d, x equals d plus L. So E equals to the integral of dE. Okay. Take the common factors out. Negative k lambda integration dx over x squared. Again, x goes from d to d plus L, so it's d to d plus L. It's an easy integral to calculate. Ke lambda. As you know, the integral itself will give you negative 1 over x squared, actually negative 1 over x, and the negative cancel with that negative sign, so it's just 1 over x going from d to d plus L. Okay, and then that means k lambda 1 over d minus 1 over d plus L. If we work it out, it's an overall negative sign. K lambda d plus L minus d, that's L, and then d times d plus L. Right? Now, of course, lambda times L, what's that? Lambda times L, that's just q. So I can rewrite this as negative k q over d times d plus L. That is our final answer. Quite simple. Okay, the textbook has the same example, except the coordinate is slightly different, so their E is positive because it's along the positive x direction. Otherwise, it's the same expression. Now, after we did this calculation, let's check if it makes sense. The very first thing you always want to check is, does it have the correct dimension? Right? It's an electric field, so we should go like K times charge divided by length squared. It's always like that, no matter what kind of electric field it is. You have K times Q, which is good, divided by length squared. Is that length squared? Yes, it is D times D plus L. That's correct. If you, for some reason, find D squared times D plus L, you can tell yourself it must be wrong, unless you have another L or whatever to cancel with that. Okay, so dimension is the first thing you check. The second thing you check is, does it make sense under special circumstances? Okay, we don't really know how to what the expression for the electric field of a rod is, but we do know that if the size of this rod were to become 0, in other words, L is 0, okay, so the entire rod shrinks to a point right here, then you know what the answer is, right? Shouldn't that be just KQ over D squared? Okay, so you take that L and let it approach 0. You're supposed to get KQ over D squared with a negative sign. Is that what you get? Yeah, that's exactly what you get. So in other words, if for whatever reason you get a 2 here, that must be wrong, because when you take L equal to 0, you don't go back to the point charge case anymore. So that's something we check. Okay, another interesting case is when D approaches 0 here, but L does not. When D approaches 0, so basically you put that point P right here, you find that the expression E goes to infinity. That's interesting. Okay, and why does that happen? It's because when you put a point here, part of this rod is very, very, very close to that point, so they can produce an infinitely large electric field. So, you know, it still makes sense. Okay, so this is our first example of a continuously distributed electric field. How does a continuous charge produce an electric field? This is the one-dimensional case. Now, next, let's take a look at a two-dimensional case. This is a famous example. It's also in the textbook as well. It's a ring and a disk. We start with a ring. Okay, so this is a uniformly charged ring of radius A. Okay, the total amount of charge is Q. All right, and this axis is its axis of symmetry. So it goes through the center of the ring and is perpendicular to the surface of the ring. I'm looking for the electric field of a point P, a distance x away from the center of the ring on its axis of symmetry. On its axis of symmetry. Okay, so how does one calculate the electric field at this point? Well, first thing first, due to the symmetry, remember it's a uniformly charged ring, okay? Due to the symmetry of the system, can you tell me the direction of the electric field at this point? Should it point like this or like that? Well, remember, this is rotationally symmetrical. In other words, you turn this thing about its axis, the electric field should be the same, right? Should not change at all, right? What does that tell you? It tells you that the electric field can only be along the x-axis, right? Because it points away from the x-axis. As you rotate about the axis, the electric field will change direction, will turn around as well, which does not make sense. Okay, so the symmetry consideration tells us that the electric field must be pointing along the x-axis. Of course, it can also point along negative axis if Q is negative. Alright, now, next, let's see. If this is a continuously distributed charge, I must start by cutting into infinitesimally small pieces, find dE, and add them up, right? So let's start with dE here. This dE from this little piece here, dQ. Okay. This little piece here will produce an electric field along that direction, right? dE. And this angle is theta. Okay, this angle is theta. Now, even though dE does not point along the x-axis, when you add all the dE's up vectorially, the final result E must point along the x-axis. That tells us that there is no point for us to add the dE up except to find its x component. If this is the x-axis, all we have to do is to add the x components of dE up, because the y and z components eventually we're just going to cancel out. Okay, so what is dEx then? Well, dEx, okay, dEx is dE times cosine theta, right? You have to integrate over dEx. You don't have to worry about dEy, dEz because they will add up to 0. So what is the magnitude of dE then? Well, it's just from a single point charge, so we know what the answer is. It's k dq over this distance squared, which is r squared, okay, which is r squared, and then cosine theta. And what do we do next? All we have to do is add all the dEx's up. And the nice thing about that is all the dEx, the x component of this dE, they all point along the positive x direction. So once again, I'm dealing with a scalar integral. So therefore, E is just the integral of dEx, right? And what is that equal to? Well, we integrate over this. So k is a constant, and then cosine theta over r squared, and then dq. Now, let's integrate. If you go around the entire ring, you find, does theta change? Well, it doesn't. What about r? R doesn't change either, right? So all of these are actually constants, and take them both out, you're left with dq. Integration over dq for the entire ring, what do you get? Don't you just get q? Okay, so this just equals k q cosine theta over r squared. That's all there is to it. Now, if you wish to express this in terms of given constants such as x and a, you can easily do that because cosine theta is just x over r. So this is just x, write it x over r to the power 3, and r itself is the square root of a squared plus x squared. So it's x squared plus a squared, the whole thing raised to the power 3 over 2. That is our answer. Okay, that's our answer. And once again, you can check for dimension and check for special cases. Dimension. Here is x to the first power. Now you better hope that this whole thing goes out, becomes x to the third power, length to the third power. Is that right? Yes, it is, because it's squared and then 3 over 2. So overall, it's length to the third power. Here, length to the first power, so overall it's 1 over length to the second power, which makes sense. Okay. Secondly, let's look for special case. What kind of special case can you think of? Yeah. If I shrink the entire ring to a point right here, which means I take a equal to 0, I will obtain the expression for a point charge, right? A distance x away from it, the answer is k q over x squared. So you take take a to 0, you get x to the power 3 here, so overall it's k q over x squared. So the answer is correct for the special case. Okay, so that is the case for a ring. Now, what if it's a solid disk, not a ring? So you think of a solid disk of a certain radius. How does one find the electric field at that point? Well, you don't have to start from scratch because you already know the expression for a ring, right? And you can think of a disk as made of a whole bunch of concentric rings like an onion, right? For each layer, it's a ring. So you know what the electric field is. And all you have to do is add the contribution from each ring up. Then you'll get the electric field of an entire disk. And we can do that. Okay, so now I have a uniformly charged disk. Total charge is Q. The area of the disk is A. The charge uniformly distributed over the entire surface. I can now define what's called a surface charge density, Q over A, and that is defined as the amount of charge per unit area, which we call it sigma. Now, again, we know how to calculate the electric field produced by a ring. And if you consider this disk as made of a whole bunch of concentric rings, each ring produce a field dE at the point P, which we calculated before, then all you have to do is add all these dEs up. Then you get the contribution from the entire disk. Okay, so what is dE equal to? dE equals to, let's copy from what we got before. So what was the result before? Okay, here, the previous page. It was equal to kqx over this, right? X is the distance between center of the ring and point P. And what about A? What about A? A was the radius of the ring. In our case, we call it R. Okay, we call it R. So if you copy that, if you copy that, would be Ke times x. Instead of q, I must use dq now, right? I must use dq now. And I divide this by x squared plus, instead of a squared, I now call it r squared. R squared, okay? To the power 3 over 2. I don't have to recalculate everything. All right. I now wish to integrate over dE to get contribution from the entire solid disk. But before I can do that, once again, I have to do some change of variables. I don't want dq. I want dr, right? So I can integrate over r, over small r. How is dq related to dr? Well, dq is the charge content in this little area. But the charge is uniformly distributed, in which sigma is a constant. So I can write dq equals sigma times what? Times this little area of the ring, dA, okay? So that's sigma times what? What's dA? 2 pi r, the circumference of the ring, times the thickness, which is dr from here to there. It's dr, okay? So it's 2 pi r dr, which I then plug into here. Then I get dE equals to kx, and then 2 pi, then sigma, and then 2 pi r dr, okay? And then I divide this by x squared plus r squared raised to the power 3 over 2. That's dE. So what is E equal to then? Well, E is the integration over dE. So E equals to the integration of dE. And then, of course, I have to integrate over r, which is from 0 to big R. Okay, from 0 to big R. So it's from 0 to big R. This integral, I'm not going to do it here. It's in a textbook, and also I'm sure with some manipulation you know how to do that. I'm going to take the constants out. It's kx sigma times 2 pi, okay, and then 0 to r, and then what's left is r dr, and over here is x squared plus r squared to the power 3 over 2. It's quite simple to do. You move that 2 in. The 2r dr is just d of r squared, and you can define r squared as a new variable, and then you define x squared plus r squared as another new variable. So you can then finish the calculation accordingly. And the answer, I'm going to write down the answer, okay, to save some time. It is equal to 2 pi k sigma, and then here's the answer: x divided by its absolute value minus x divided by x squared plus r squared to the power 1/2. Make sure you know how to do that. You know how to finish this integral. Okay, look at the first term here. The first term only, it's either positive one or negative one depending on which side of x you're on. If you are on the positive side, so this point P right here, this is positive x direction, it's just x divided by itself, so it's 1, okay? If you're on that other side, x is negative, absolute value of x is positive, so you get negative 1, that's all. Okay, now, imagine what happens when the radius becomes very, very large, okay? When the radius, big R, approaches infinity. So you don't have a disk anymore, you have the entire sheet, infinitely large sheet, okay? Do you get an infinitely large electric field here? Well, let's see. If you take R to infinity, then what happened to the second term? It's gone, right? It's 0, right? Because R is in a denominator. So when R approaches infinity, you don't have the second term. You just have 2 pi k sigma x divided by x to absolute value. So let's assume that x is positive. Okay, so this is just 1. So it becomes 2 pi k sigma. Okay, strangely enough, you get a constant. In other words, when you look at the electric field of an infinitely large, uniformly charged sheet, it doesn't matter how far you are from the sheet. No matter what x is, you always get the same exact electric field. You can move further away from it, the field is the same. Okay? And it's a very simple result, even though we took a lot of effort trying to get this. We are going to revisit that same problem in the next chapter, and we're going to see how we can obtain this result without all this complicated integration. Okay? We can get this result in a matter of a couple of minutes or even shorter using a different method based on what's called Gauss's law. But this result itself is interesting and important.